Welcome, and this is the module 5, that is week 5 and lecture number 23, and in this lecture I will talk about the blast furnace productivity. And major concept that will be covered, that is, first of all I will discuss about evolution of the furnace dimension, because to increase the productivity the blast furnace has grown its size over the years. So I will talk about that, what is the trend, how the blast furnace dimension has changed over the years. And then I will talk about the definition of specific productivity indices, that is, how do you compare the performance of blast furnace irrespective of its size. And then concept of productivity, actually productivity depends on which major parameters, and how to improve the productivity in the blast furnace, and what are the measures that we have to take while considering the increasing the blast furnace productivity. That is what are the measures we will take to increase the productivity, that we will discuss in this lecture. Now first, if you see the evolution of the blast furnace dimension over 1960 to 80s, because during that time there has been significant increase in the blast furnace dimensions. After that it has increased, but not that significantly, because already the blast furnace has grown to 4000 meter cube by 1980 only, and after that it has increased up to nowadays it may be around 6000 meter cube blast furnace is also available. But the major growth from starting from say 64 meter cube to 4000 meter cube has taken place during this time. Okay, and if you see the increase in the size, you can see this is the heart diameter. Heart diameter has increased from, it is given in millimeters, so 900 millimeter, that means 0.9 meter to it is 14 meter. So heart diameter has increased significantly, 0.9 meter to 14 meter, while the height also has increased. It has increased from 15 to 36, around 2 times. That is, the height has also increased 15 meter to 36 meter. And today the productivity also increased from 25 ton hot metal per day to 10,000 ton hot metal THM per day. Okay, so this has increased, and if you see the increase in the height, because it is not that the blast furnace has not increased only axially, you can see it has increased laterally also, and the lateral increase is quite significant, because 0.9 meter to 14 meter in diameter increase. So the area increase also, there is a hearth area increase also significant. So it has not only increased in the axial direction, and lateral increase you can say more compared to that of the axial. And this is because if you increase the height, then overburden on the blast furnace increases, and also the burden, all the burden material has to move a longer distance, and you see when the burden moves in a longer distance, lot of abrasion, and this, as a result, chances of fine generation become more, and the maintaining the permeability become very difficult unless you have a very good burden material. And already the burden material has increased its strength, but if you go on increasing the height, that strength may not be sufficient. Okay, and eventually when they are coming down to a longer distance, so they will create the dust, and bed permeability will be affected significantly. And that is one problem. And so that's why it has increased in the lateral also, and the lateral increase is significant compared to that of, you can say, this thing. Again, if you increase the laterally, that is in the your, what is that called, if you increase laterally this direction, then what happens, the dead man coke increases, because raceway cannot penetrate much into the center as compared to the increase in the hearth diameter. So if I just draw it, that is lateral increase, one problem is there. Suppose you have this is the raceway like this is the raceway, and you have the dead man cokes here. Suppose this is the dead man coke, and this is for a bigger one. A smaller one also, if you see, then also you have a raceway, and this is the dead man coke. So you can see there is the increase in the dead man coke area. So dead man's coke increases because raceway cannot penetrate too much inside the axis of the hearth. Okay, so as a result, some of the hearth area even unutilized and the dead man inactive coke area increases. So, okay, that is also another problem. If you go on increasing the laterally, you cannot burn much of carbon as compared to the increase in the hearth diameter, okay, because ratio is high, is cannot increase significantly. It has a limitation. Beyond that, it cannot penetrate into the axis. As a result, your dead man's coke, inactive coke increases. So, that is another problem if you want to go laterally, and axially you have problem because that is the major problem. Axially you cannot go very long distance blast furnace because the material has to travel a longer distance. Eventually they will create the fine generation and the bed permeability will be affected significantly, right. So as a result, that is why I tell you, there is a furnace expanded more laterally than axially. Axially is not that much, laterally they have also increased. And as I said, this is the furnace production, but the modern large blast furnace can reach productivity of 10,000 to 13,000 tons per day today. So today you can have more generation, there is the more ton of hot metal per day you can produce, and the volume, blast furnace volume also has gone to around 5,000 normal meter cube, size 5,000 meter cube. So up to 80s it was around 14,000. Now up to 80s it was, the furnace volume was around say 4,000 meter cube, as you can see, and that has increased today to 5,000, so 1,000 more. So major development has taken place from 1960 to 80s. After that also now some bigger furnace is coming, even that is the thing. So today also India also some 4,000 to 5,000 meter cube, in this range some blast furnace are coming by Jindal Steel in you know about in Angul, and then Kalinganagar, there is the Tata Steel, all are of and of 4,500 meter cube or of this range. So if you see the size and number of the blast furnace in the world in 2007 data, and it is taken from the Amit Chatterjee lectures in IIT Kharagpur for PGD steel lecture in 2009, and if you can see, that is the number of furnaces and their volume, corresponding volume. So 0 to that time in 2007, so you can see 500 meter cube furnace, 0 to 500 meter cube furnace was the maximum 130, okay, and as the furnace volume is increasing, so number of units of blast furnace over the world was decreasing, okay, and 5,000 to 6,000, that is why it was only 4, and then so big furnace are very limited, much bigger size. So those are limited actually, and nowadays this size is 4,000 to 5,000, this range, that is the furnace are coming up even in India, as I said. So some of the furnace, several blast furnace in the size range 4,000 to 4,500 meter cube have been added and will be added in future even in India. So some of the bigger furnace are coming. Even in the China, a lot of 4,000 meter cube furnace has come, but by China's large productivity, not only due to very big furnace, but they have several small size furnace. So that's why their productivity is also high. But bigger furnace is there. But major problem with the bigger furnace, as I said, that is the burden material, a very stringent burden material, because it has to increase little bit axially also. So your burden material quality cannot be compromised. It should be very strong, and also as I said, because of lateral increase, there is a limitation of the ratio penetration towards the axis of the hearth. So that limitation is there. So considering this thing, this is the evolution of the blast furnace dimension over the years. Okay. Now let us go to, that is the now thing is that how do you compare a big furnace and the small furnace? If you say ton hot metal per day, that you can, obviously a bigger furnace will produce more ton of hot metals than compared to the smaller furnace because of the volume difference, right? But if you want to compare the performance of the blast furnace irrespective of size, then you have to bring in the term specific. So specific productivity indices is required. There is the per unit volume or per unit hearth area, like that. So that is the productivity, this number 3, this productivity based on unit volume of the working furnace. This is the most used specific productivity index that is used, and you can see this is basically ton of hot metal per meter cube per day, THM per meter cube per day, and that is a very popular specific productivity definition, and its value maximum is 3.5. 3.5 is that very good blast furnace performance wise. Okay, and you can find the distribution. Okay, there is the heart diameter. If you are increasing the heart diameter, obviously this is slightly increases like this. Okay, so with heart diameter, your productivity, how it is increasing. So you can find this is a very good value. There is the 3.5. 3.5 is the maximum value. Okay, so another is there, that is if you define in terms of, that is the productivity based on the hearth area. That is the, if you increase the hearth area in compared to the hearth area, the specific, that is the ton hot metal per unit area of the hearth per day. So then one definition is there, per unit area of the hearth. And then also its value, best value is around 70. If you have a about 70, then it is the quite good value. Then another definition is there, that is the volume utilization coefficient, KIPO, and this is basically defined as the, that is the useful volume, that is the meter cube of, that is the volume of the blast furnace per ton hot metal per day. That is the volume of the blast furnace used to produce per ton of hot metal per day. That is defined as the volume utilization coefficient. That is called the KIPO. So KIPO value is around best is 0.28. That is the volume utilization, right? Normal meter, there is the meter cube per THM per day. Another definition is there, that is called the specific coke consumption rate. Here basically how much coke you are consuming per unit volume of the blast furnace, useful volume, that is the meter cube. I am talking about the useful volume, per meter cube of useful volume per day, and that is defined as the specific coke consumption rate. Okay, and its value is around 2, is supposed to be very good. Okay, so that is different specific productivity indices, and as I said, among them the most useful definition is this one, third one, the productivity per meter cube per day. Okay. Now let us come to the concept of productivity, because I say, because this productivity and what are the parameters on which this productivity depend, and how to increase the productivity of the blast furnace, or what are the factors that influence it and how to control them, right? So now the productivity you can write in this form Q by K, where Q is called the coke throughput, that is the kg of coke that you burn per day, that is called the throughput, and coke rate divided by the coke rate, and in the denominator you have the coke rate, and coke rate is basically kg of coke used per ton of hot metal. So here the rate not with respect to time but respect to the hot metal. So amount of coke consumed per ton of hot metal, and Q is basically the coke throughput, that is per unit time how much coke you are consuming in the blast furnace, right? So then Q has a unit, obviously you can see kg per day, and K has a unit of kg per THM. So P, whatever you are getting, it is coming THM per day, ton of hot metal per day you are producing. So if you want to produce a certain ton of hot metal per day, it depends on Q and K, where Q in the numerator, K in the denominator. So what you have to do, if you want to increase the productivity, you have to increase Q, but you have to decrease K. You have to increase Q and you have to decrease K. So if you do that, then your productivity will increase. So that is the thing. First of all, you can take from here, that is what you have to increase this and you have to decrease this, and then your productivity will increase, right? So this is what I wanted to say. There's the productivity will increase, coke throughput you have to increase. Now see what are the parameters that affects the coke throughput in the blast furnace, and K coke rate, I have to reduce the coke rate. What are the parameters that will be? That I will come to the next slides. Okay. Now see the coke rate and productivity. Thing is that P is equal to K by K, as I said. If I can decrease, again I am writing it, if I can decrease this, I can increase this. So this is what I am going to do. Now how to reduce the coke rate in the blast furnace? Now burden preparation has a great role to reduce the coke rate. We have discussed previously also. And what is this burden preparation? Burden preparation means you can do the beneficiation, right? When you do the beneficiation, what you can do, you can decrease the gangue constituents, there is the gangue into the ore, right? As a result, what will happen? The slag volume produced into the blast furnace will be less, and if your slag volume is less, it will obviously decrease the thermal load of the blast furnace, because slag contains lot of sensible heat and that goes away along with the slag. So that as a result, it takes lot of heat from the blast furnace. So if your gangue is less, slag volume is less, obviously you can decrease the thermal load of the blast furnace. That is the second point what it is telling. Okay. And then you can do the prefluxing. For example, sinter. When you are making the sinter, we are adding the lime with it. So as a result, what happens? You can produce two type of sinter, as I said. There is the flux sinter as well as superflux sinter. Flux sinter take care of its gangue material, and superflux sinter, after taking the gangue of the sinter, it can take care of the gangue that is coming from the lumpy ore and others, which are not prefluxed. Okay. So as a result, the blast furnace become sufficient with respect to the lime when you charge the sinter, and you don't require to charge limestone additionally. And limestone addition is a thermal load in a blast furnace, because decomposition of the limestone is a endothermic reaction, so it requires it, right? So if you can avoid charging the limestone by using the prefluxed burden like flux sinter, superflux sinter, obviously you can reduce the thermal load of the blast furnace. Okay. Another thing is that increased blast temperature. If you increase the blast temperature, then the blast is carrying a lot of sensible heat along with it. As a result, it also reduces the thermal load of the blast furnace. So, and you can see, and what are the other three parameters that you can find? There is the preflux agglomerate also increase the indirect. Now you can see this is the decrease in the thermal load. Obviously, if you can decrease the thermal load, you can decrease the coke rate, because thermal load decrease means less coke is required to generate the heat, right? Similarly, if you can increase the indirect reduction, okay, then also you can reduce the coke rate, because in both the indirect reduction, that is, you are utilizing the blast furnace gas more effectively. Okay, there is the CO utilization is more, that is the blast furnace gas, that is CO is produced, you are utilizing effectively. As a result, your coke rate will be less, per ton of hot metal coke amount will be less. Otherwise, if you cannot utilize, most of the CO will leak to the atmosphere. So you are not being able to utilize it within the furnace. So what you have to do, basically, if you want to increase the CO utilization, you have to increase the the indirect reduction in the blast furnace. You have to convert the CO to CO2. Okay, when the CO is taking 1 mole of ore oxygen, then it becomes CO2, it becomes saturated with the oxygen. That is the maximum extent the carbon can take the oxygen. So you should not leave the CO to the atmosphere. You must use the CO to take out one extra ore oxygen such that it becomes CO2 and leave the furnace. So that is CO to CO2 conversion is indirect reduction. So you have to increase the indirect reduction. How you can do that? So this is also, if you have a preflux agglomerate, then basically increase the indirect reduction. How? Because we have seen when from the sinter mineralogy, when the CO to SiO2 ratio increases or the basicity of the sinter increases, then your glass is replaced by the calcium ferrite, and which increases the reducibility as well as strength. How it increases the reducibility? Because it becomes a very porous structure. Okay, so fluxed pellets, fluxed agglomerates are basically porous and they are very reducible. Okay, as a result, your gas solid interaction will be to the maximum. More the reducible, that is the gas utilization will be more, because gas will be much faster utilized by reducing the iron ore. Okay, so that is one thing. And improve gas solid contact, that is very important. And improve gas solid contact also in the blast furnace, if you want to improve it, then also burden preparation is required, like sinter, pellet. They are stronger burden material and they will offer more permeability to the bed, right? So as a result, more permeability means you can have a more indirect reduction. Gas solid contact will increase, as a result indirect reduction increases. So there also burden preparation has a role. Not only burden preparation, burden distribution also has a role to maintain the bed permeability, as we have discussed previous class. So burden distribution, burden preparation both can improve the bed permeability. As a result, you can have more indirect reduction. Another point, you can find use of hydrogen bearer. Hydrogen bearer means, that is, you can inject some steam or oil injection, all gives the hydrogen. into the blast furnace. So how does hydrogen help in the indirect reduction? Because as I said, hydrogen is a much better reductant than CO, and you can see that is the reducibility of the ore increases around 4 to 5 times if you use the hydrogen, because hydrogen is very efficient both thermodynamically and kinetically, right? So if we can introduce some amount of hydrogen into the blast furnace, obviously indirect reduction will improve, right? So all these things, that is the hydrogen bearer, improve gas solid contact, preflux, agglomerate, they will increase the indirect reduction in the blast furnace. And prefluxing, beneficiation, increased blast temperature will decrease the thermal load of the blast furnace, and both will add to reduce the coke rate. Thermal load, coke rate will increase, indirect reduction, you are utilizing the blast furnace gas more effectively, coke rate will decrease. Another thing is the fuel injection. If you do some fuel injection, then also coke rate decreases, because if you do the fuel injection, some function of the coke is supplemented by fuel injection. For example, heat generation and the reducing gas generation, fuel also can do that. So you can reduce the coke rate to some extent if you do the fuel injection, because some of the coke function is supplemented by, can be met up by the fuel injection. So you can reduce the coke rate. So that also another way you can reduce the coke rate and then increase productivity. Okay, so that is the thing, that is if you want to increase the productivity. Now how the coke rate increase the productivity, I just forgot to mention, because if you reduce the coke rate, what happens per ton of hot metal, you reducing the coke, obviously you are making space for the more iron ore to be charged. Okay, so that's why you can charge more iron ore and you can produce more iron. That is the coke rate if you decrease. Okay, so space you are creating. Okay, because, and also the slag volume will be less. If you reduce the coke rate, slag volume will also be less. As a result, your space in the blast furnace for iron production will be much higher. Okay, so all these things basically, so if you can decrease the coke rate, you obviously increase the productivity, right? So this is the coke rate, and now let's see. Now you see the coke throughput and the productivity. Now how you can increase the coke throughput inside the blast furnace? This is a problem, aerodynamic problem, as I said. If you want to burn more amount of coke per unit time, you have to use a higher air blast, right? And if you use the higher air blast, then the aerodynamic problems crop up at that time, because the pressure drop increases in the dry zone and the pressure drop increases everywhere. As a result, what happens, the dry zone you may have a channeling, and in the wet zone you can have a flooding tendency. So just increase the productivity, increase the blast rate, it is not a direct equality. You have to think about the aerodynamics of the furnace much more deeper, and then you can take that. Now I have just discussed, that is the, if you want to increase the productivity by increasing the coke throughput, then how you can do that. Now if you want to increase the coke throughput, that is you want to burn more amount of coke per unit time, then you have to supply more amount of oxygen per unit time. That is obvious, because a certain amount stoichiometrically, if you want to burn certain amount of carbon, certain amount of oxygen is required. Now you are burning carbon, you want to burn carbon per unit time, more carbon per unit time, you have to supply more oxygen. Now if you want to give the more oxygen, what are the measures you can take? In the blast, you are increasing the oxygen input in the blast. It may be by oxygen enrichment, it may be by increasing the volume of the air blast, right? You can increase that. So what are the measures? How you can increase the oxygen input into the blast? That is one thing, is that increase blast volume. That is obvious. That is the first thing come to my mind. If I want to increase, if I want to burn more carbon per unit time, I have to give, I have to increase the blast volume per unit time. Blast rate I have to increase. That is the, whatever the blast is going per unit time, I have to increase, then oxygen will increase, right? Another thing is that humidified blast. If I give the humidified blast, then also supply the oxygen, because H2O contains obviously oxygen. Or oxygenated blast, I am replacing some amount of nitrogen from the air. Okay, so now usually the volume percent of oxygen is 21 by volume percent. If I give some extra oxygen into the air blast, it can be 23% oxygen, 77% nitrogen, or 25% oxygen, 75% nitrogen. So this way I can increase the oxygen input into the blast. Now oxygenated blast, no problem. Humidified blast, you just inject the oxygen, moisture, that is possible. But if you increase the blast volume, that is not that easy. That was talking at the beginning. So if you want to increase the blast volume, then the pressure problem coming, the pressure drop will increase. Now how you can do that to tackle that pressure drop, because pressure drop will increase. To tackle that, what you can do, you can increase the stroke permeability. That is one thing, you can increase the stroke permeability. If you increase the permeability, then if you give more blast also, then that will be taken care of, because then the energy loss, friction loss will be less, permeability, bed is more permeable, so pressure drop will not increase that much. Secondly, you can use high top pressure. If you have a high top pressure, because pressure drop is basically P1, bottom pressure minus top pressure. If you increase the top pressure, pressure drop will decrease. And we have discussed. So these are the two ways you can decrease the pressure drop. That is, you can use more blast rate, but without increasing the pressure drop. Now, high top pressure is okay. Now, increase stroke permeability. If you want to increase the stroke permeability, what you have to do? One thing is that you can see the burden preparation. Obviously, you can make a more stronger burden, okay, burden preparation, or you can increase the coke strength. That is the burden. By burden preparation, you can do that thing. Burden preparation, basically, we are talking about the wood strength as well as the coke strength both. So here, basically, burden preparation, we are talking about the wood strength, how we can increase the wood strength. Then we can do the that is the beneficiation. If I do beneficiation, slag volume will be less. If slag volume is less, then that the lower part of the furnace in the wet zone pressure drop will obviously decrease, because thinner is the wet zone, less is the problem in the blast furnace. Okay, you can decrease the pressure drop also, because liquid is less, because liquid going to the pores and blocks the pores, and it gives a lot of resistance to the gas flow, right? So lesser the slag volume, better is life. So better is the bed permeability. And also increase mechanical strength. If your strength is high in the dry zone, when the burden comes down, then they will not generate fines, not of fines. As a result, dry zone permeability will also be good. And if you decrease the slag volume, wet zone permeability will be good. And lower slag bulk, obviously, that is the thing is there. So by burden preparation, obviously, you can increase the stroke permeability both in the wet and the dry zone, and increase coke strength. That is also very important. You have to increase the, if you can increase the coke strength, that also similarly help into the bed permeability. So all this thing basically leads to higher coke throughput. So if you want to increase the coke throughput, then you have to take care of, consider this burden preparation, and then all this thing what I have discussed about oxygenated blast, humidified blast. Okay, so these are fuel injection. And then finally you can see that is the coke throughput, okay, increases. And then here I have added one fuel injection also, because if you increase the fuel, there is the coke throughput, you can increase the that is obviously the permeability. Also nowadays it is not only the coke that is charged into the blast furnace, you have a fuel also. Fuel also generate the heat that can also produce, that is the melt some more iron into the blast furnace. So as a result, your fuel injection has been added also. There is a fuel injection also will lead to higher productivity. When you add some auxiliary fuel, they are generating extra heat. So that extra heat also can melt some extra iron, and reduce and melt some extra iron, can produce more iron. So it is the increased coke throughput as well as the fuel injection. That's why we added separately. That will increase the productivity. Okay, fine. So now another thing is that now minimum coke rate, if I just want to explain, that is the how do you get the minimum coke rate with respect to the what is that, our Ridge diagram. So Ridge diagram, one thing we said, that is I will just talk about this thing, that is the Ridge diagram. If you remember, that is we have talked about. So this is the Ridge diagram, and we have seen there is a Woodstide reserve zone. Here is the zone is there. Woodstide is the chemical pinch point is there. Okay, this is the optimum coke rate, but actual, and this is the thermal pinch point. Actual blast furnace may operate like this. So this is some blast furnace. Okay, not very big. This is the optimum coke rate. Suppose this is an actual blast furnace operating like this. Some blast furnace is operating like this. Okay, so you have a chance that you can move this to here, that is you can shift this point. I'll just draw a little, because this is 1 minute, just this is another diagram we can show, this is another, and it may be, it is a very bad diagram, yeah. Diagram wise also, this is coming to this point. If I say this is the Woostite point, okay, maybe there, this is the Woostite, Fe 0.950. So this is the Woostite point, this is the Woostite. So you can find, you can move, suppose one furnace is a, so you can move this point, shift to this point, that is this point, that is this point you can shift to here, or this point you can shift to here, because Woostite reduction, you can find here the Woostite iron equilibrium has not been attained in this point, here it is there. So you can reduce the coke rate, you have a scope of reducing the coke rate, minimum coke rate if you want to attain, you have to increase this Fu equilibrium, you have to achieve this equilibrium, this is the equilibrium line, that is the optimum line, okay. These are the sum of the blast furnace I have shown. They can, line can be like this. So their improvement, performance can be improved if we can shift this point to here or this point to here. So this point has to be seated on the right hand side. So that means what you can do by increasing the reducibility of the sinter or reducibility of the iron ore, if you can attain the, what is that called, this is the chemical equilibrium of FU-Fe system, FU-Fe chemical equilibrium if you achieve, that is if you can maintain a chemical reserve zone, then you can get an minimum coke rate. So this is very important, attaining the Woostite Fe equilibrium in the upper part of the isothermal zone. So to do that, what you have to do, you have to increase the reducibility of the iron ore burden, that is one thing. And then reducing the heat demand, another thing is that if you can see the slope can be decreased, here this minimum slope, and also you can decrease the slope further if your this point is moving up. If this point goes up here somewhere, and then you can have another line. So if your heat demand decreases, then this point will move up. In that case also you can further low, that is the coke rate, you can further reduce the coke rate. So if you can decrease the heat demand also, then this point, thermal pinch point, will move up. As a result, you can have a further lower coke rate. So for that, how you can do that, reducing the heat demand, you can restrict the heat loss. The two things is that, one thing is that Woostite iron equilibrium you have to attain in the chemical reserve zone. Another thing, if you can reduce the heat demand also, you can further lower the coke rate, okay. So one thing, what to reduce the heat demand, what you have to do, basically the decomposition heat will be there, that is you cannot do anything, and what is in your hand is there, and sensible heat, decomposition heat, that will be there, iron. But what is in your hand is restricting the heat loss through the exit gas heat loss. So you can maintain a proper, what is that called, heat capacity of the gas, not too much heat capacity in the upper zone, then it will take away a lot of heat with it. So oxygenated blast or oxygen enrichment can be helpful to some extent, sometime, okay. You can do that, then you can restrict the heat loss through the exit gas. And also how you can do that, and another point, restricting the heat loss to the furnace wall, that is also very important. There is a furnace wall, lot of heat can go out, so if you can restrict that. So for that you have to consider the refractory breaks. So I'll talk about the refractory breaks in the blast furnace, okay. So for basically refractory break, main purpose is to containing the heat. Besides, refractory break also has other purpose. What are the purpose? That is the carbon monoxide attack, action of the alkali and vapors at high temperature, abrasion by moving solid charge, and attack by the molten slag and metal. These are refractory are subjected to, and this is the function of the refractory obviously, but it is another function is the containing the heat, such that you don't allow the heat to go away. In that case, your heat demand of the furnace increases. And what are the refractory? That's why it is used. Basically, ordinarily the fire clay bricks containing 40 to 45% alumina used in the upper stack, and heavy duty fire clay brick, that is the containing more amount of alumina, around 60% alumina, that is used in the lower part, stack, belly and the boss region. Okay. And carbon lining is used mostly into the, that is the heart region. Okay. So these are the refractory lining is there. So we have to take into account this refractory erosion of the refractory. For example, when the heart lining erode away, then a lot of heat can go through the furnace, that is the from the heart region. So refractory lining, maintaining the proper health of the refractory lining is very important, such that if the refractory lining erode away, obviously your heat loss to the atmosphere will be very high, heat demand will increase, obviously the coke rate will increase, productivity will decrease. So all these things has to keep in mind. So these are the some reference, and I will talk about the conclusion what I said. That is, the productivity in the blast furnace can be increased by decreasing the coke rate and increasing the coke throughput. That is the thing. And as I said, that the burden preparation, burden distribution, and then use of hydrogen bearers and fuel injection can reduce the coke rate. And if you want to, and burden preparation, high top pressure, auxiliary injection, all can increase the coke throughput. As I said, if you want to increase the coke throughput, you have to give more air blast. As a result, you have to consider the hydrodynamic condition into the blast. There is the aerodynamic condition in the blast furnace by high top pressure or increasing the permeability of the bed. And permeability of the bed, if you want to increase, obviously you have to take care of burden distribution, burden preparation, and also some auxiliary injection like your fuel injection, and then those also supplement the coke function. As a result, you can increase the productivity also, because you are generating some extra heat, some extra reductant by your auxiliary injection, and also sometimes the better reductant like hydrogen. So you can increase the productivity obviously. And in terms of this diagram, as I said, minimum coke rate can be achieved by achieving that thing is there, that is the FU equilibrium in the chemical reserve zone you have to achieve, and for that the reactivity of the iron ore should be high, such that we can ensure the blast furnace contain a chemical reserve zone such that you can get a low coke rate. And also you can reduce the coke rate further if you can decrease the heat demand of the furnace, and that can be done by restricting the heat loss through the wall as well as through the exit gas. And for that you can use oxygenated blast, or you can use the refractory, and you can properly monitor the health of the refractory such that the heat loss doesn't increase to the atmosphere to a significant extent. Okay. So with this, I will basically close this lecture. Thank you very much.